Line Commutated Converter, or LCC, HVDC systems operate as massive power corridors. They are highly trusted, mature technologies used to bridge distant regions, transferring bulk electricity across hundreds of miles with minimal loss. To function safely, these systems traditionally operate by enforcing a rigid, constant DC link voltage. This isolates the sending and receiving AC grids, preventing electrical disturbances on one side from cascading to the other. That isolation becomes a liability when large-scale renewable energy sources, like offshore wind farms, connect to the sending end grid. These sources introduce highly variable power outputs that constantly perturb the local electrical frequency. Because traditional HVDC setups act as passive pipelines locked to a constant voltage, they ignore these fluctuations. They leave the entire burden of grid frequency regulation to the local synchronous generators, physically located on that specific side of the link. We can change how the hardware behaves by abandoning the constant DC voltage constraint. Allowing the voltage to fluctuate utilizes the fast switching dynamics of LCC converters for bidirectional, real-time grid frequency regulation. To achieve this, researchers designed a linear quadratic Gaussian, or LQG, optimal control strategy. Instead of fixing the DC voltage to a rigid set point, this controller dynamically regulates both the DC voltage and current simultaneously. Varying the DC voltage enables the DC link to function as a grid-stabilizing asset. It forces both interconnected grids to pool their generation resources and share the kinetic burden of a transient disturbance. This schematic maps the physical topology of the proposed system. We have the sending grid, labeled Grid 2, on the left, connected through a rectifier, and the receiving grid, Grid 1, on the right, connected through an inverter. The strategy assigns specific tasks to distinct hardware terminals. The rectifier terminal explicitly controls the DC link voltage. Meanwhile, the inverter terminal is strictly responsible for controlling the DC current. To give the converters the ability to emulate physical inertia, derivative controllers are integrated at both terminals. These read the local rate of change in frequency and adjust the reference signals. Next, proportional droop controllers are added. They share active power between the HVDC converters and local generators, responding to frequency errors by pulling or pushing power across the link. This animated block diagram shows how those controllers interact during a disturbance. Watch what happens if Grid 1 experiences a sudden spike in load demand, causing a sharp drop in local frequency. The inverter's local droop controller reacts immediately to save Grid 1. It attempts to compensate for the load spike by pulling more power across the DC link from the rectifier. But pulling that power drains Grid 2. As Grid 2's local frequency drops, its own rectifier droop controller detects the error and reacts by attempting to cut power transmission to protect its side. The two commands collide inside the DC link. The inverter demands more current, while the rectifier attempts to lower the voltage to reduce power transfer, creating heavy power oscillations. Because localized droop controllers operate entirely blind to the conditions on the other side of the grid, their conflicting commands degrade the primary frequency control they were installed to perform. Resolving that conflict requires a centralized intelligence, a secondary frequency control system that monitors both grids simultaneously and coordinates the converter responses. This equation is a cost function. It evaluates the augmented state, or X sub E, a unified mathematical model that groups the physical plant dynamics with the integral of all frequency and voltage errors. The Q matrix contains weighting coefficients. By tuning these numbers, engineers dictate how aggressively the controller penalizes deviations in both grid frequency and DC voltage. The R matrix regulates the control effort itself. It ensures the mathematical solution does not demand physically impossible response times, preventing the generators and HVDC converters from saturating. By solving the algebraic Riccati equation, we find the optimal gain matrix, K, that minimizes this entire cost function at two terminals, to handle those disturbances and bypassing the trap of localized reactions. This chart maps pole placements on an S-plane to prove system stability. We are comparing the eigenvalues of a conventional PI controller against the proposed LQG controller. Pay close attention to Group C, the dominant pole cluster located near the imaginary y-axis. These poles dictate the primary dynamic behavior of the entire HVDC system. The LQG controller forces these dominant complex conjugate poles further left into the negative real half of the S-plane, away from the imaginary axis. In control theory, distance from the imaginary axis translates to speed and damping. A deeper push to the left means the system will respond faster and suppress oscillations heavily during a transient event. This root locus plot shows what happens when we increase the DC link inductance, denoted by the parameter L. As the inductance scales up by a factor of 100, the poles migrate rightward. High inductance traps the poles near the imaginary axis. This tilts the damping ratio, meaning any frequency deviations caused by a load disturbance will be persistent and slow to clear. To fully exploit optimal control for real-time frequency regulation, the physical plant design must favor low-inductance DC filters, keeping the electrical pathways highly responsive. We can validate this mathematics against a real-world model. Using the exact parameters of the 150 megawatt Jeju-Hainem LCC HVDC system, researchers simulated a continuous link between ascending and receiving grid. This chart shows the system's step response to a sudden 30% load increase on the inverter side. The proposed LQG trace suffers a shallower frequency dip and settles faster than conventional PI controllers, recording a 28.8% reduction in maximum frequency deviation. These two charts track the power output from generators on both sides of the DC link. Under the LQG strategy, both sets increased their output by an identical 0.15 per unit, successfully forcing the distant grid to share the local burden equally. This scope trace tracks the DC link voltage. To instantly share power across the link, the controller allows the voltage to fluctuate, but the LQG matrix strictly bounds it to a maximum variation of only 4.3%, keeping the hardware well within standard operational tolerances. Allowing that 4.3% variance places a slight, manageable stress on the HVDC hardware. However, inverse power modeling shows this is vastly outweighed by the savings in mechanical and thermal wear on the synchronous generators, extending their operational lifespans. The LQG controller resolves the decentralized droop conflict by recognizing the two separate grids and their DC link as a single, mathematically unified system. Coordinating converter firing angles through a unified state-space representation allows LCC HVDC links to act as bidirectional frequency stabilizers. As power grids integrate more intermittent wind and solar, these dynamic control strategies offer a way to manage the resulting frequency variations across wide areas.